Welcome back to Engineering Acoustics. Hi, this is Professor Ryan Harne. In the mid to high frequency range of transmission loss, coincidence phenomena may occur due to synchrony of acoustic and bending wavelengths. In this video, we'll learn about the coincidence mechanisms and what influences its occurrence.
So let's get started. As we look at transmission loss data for a wide variety of panels, we uniformly find a local reduction of transmission loss in the frequency range around 2 kHz to 4 kHz. This is the coincidence region. What are the fundamental mechanisms that result in this local reduction of transmission loss? To understand how coincidence occurs, we need to learn more about bending waves. The bending stiffness of a panel is what we've seen before. The bending stiffness D is equal to y, the Young's modulus, multiplied by I prime, the moment of inertia, divided by 1 minus nu squared, where nu is the Poisson's ratio. D has units of kilograms meter squared per second squared. Y is the Young's modulus in units newtons per meter squared. I prime is equal to h cubed divided by 12, where h is the thickness, and nu is a Poisson's ratio. Knowing the bending stiffness, we can compute the bending wave speed. Cb, the bending wave speed, is equal to the bending stiffness multiplied by omega squared divided by m, the mass density, to the power 1 on 4. This has units meters per second. The mass density m is equal to rho h, where rho is the density in kilograms per meter cubed. Knowing the bending wave speed, we can divide it by the frequency to find the bending wavelength. Lambda sub b is equal to c sub b divided by f. Of course, this has units meters. The frequency at which the bending and acoustic wavelengths are the same is called the critical frequency. When we equate lambda b is equal to lambda, what we find is the critical frequency. It's equal to the sound speed c squared divided by 2 pi multiplied square root by m divided by the bending stiffness d. This is, of course, in units of hertz, and this is the critical frequency. When the bending wavelength and the acoustic wavelength are the same. In a schematic, we see the case here. The acoustic wavelength going over this extent and the bending wavelength. They are equal at the critical frequency. If the acoustic wave arrives at an oblique angle of incidence to the panel, we then need to consider the projection between the acoustic and bending wavelengths. Consider then that the bending wavelength, lambda b, is the hypotenuse for a triangle where one side is the acoustic wavelength. So that means that lambda b times sine theta, where theta is the incident angle, must be equal to lambda. This is the case as shown here for this angle of incidence, and when the angle of incidence is less steep, we see that the acoustic wavelength is reduced. But going back to this case, by equating our bending wavelength with the acoustic wavelength according to this projection, we find that f sub b, the coincidence frequency, is equal to c squared divided by 2 pi sine squared theta multiplied by density, mass density divided by the bending stiffness, and the square root of that. As we look at this general coincidence frequency, we see that the Critical frequency is the lowest frequency for which coincidence occurs, according to this equation here. Looking more carefully at the transmission loss that occurs around coincidence, we find that the panel bending impedance is equal to the following expression. The panel bending impedance, capital Z, is equal to J, the imaginary number, multiplied by 2 pi times the frequency F, multiplied by the mass density M, multiplied by the quantity 1 minus frequency divided by the critical frequency squared, multiplied by 1 plus J times eta, which is the loss factor of the material, multiplied by sine to the power 4 of theta, and then we'll close the bracket. J is equal to square root of negative 1 as before, it's the imaginary number, and eta is a loss factor that can be determined experimentally. Given this bending impedance, the power transmission coefficient is then approximated to be tau as a function now of theta is equal to the magnitude of 1 plus z cosine theta divided by 2 rho naught c. Close the magnitude and take it to the power minus 2. Knowing the power transmission coefficient, we can then find the transmission loss. Here's one example for a variety of loss factors eta from 0.01 in the red curve to 0.05 in green, and finally to 0.1 in blue. We find that as damping increases, the coincidence phenomena reduces in magnitude. Now, considering different angles of incidence, as the angle increases from 30 degrees of incidence to 60, we find that the coincidence phenomena occurs at lower frequencies, and this in fact agrees with what we've seen with the critical frequency, which is the lowest frequency for which coincidence may occur. But since the diffuse sound field that we characterize with the transmission loss measurement, because this is incident on the panel at many angles of oblique incidence, coincidence practically will show up in transmission loss data over a frequency range from a lower to an upper limit. To see how coincidence compares between model predictions through these equations and actual data, we can plot this out for a variety of panels. Consider an isotropic panel. It's 6 mm thick glass. The transmission loss determined using the prior equations is shown here in red. The data, though, are shown in red circles. In general, there's good agreement up until where coincidence occurs. At higher frequencies, there's great overprediction by the model. Similarly, at 16 mm glass, we find that the mass has increased, the transmission loss at slightly lower frequencies has risen, and we find a coincidence dip that occurs at lower frequencies now. The data likewise agrees fairly well up until coincidence, but for higher frequencies, the model greatly overpredicts once again. Most materials, though, never achieve this theoretical 9 decibel per octave gain in transmission loss above coincidence, due to a variety of factors including the panel installation. So there are many corrections that are proposed out in the literature and by practitioners that help reduce the transmission loss above the coincidence. One correction is shown here. It also better maps the lowest point of coincidence. It's almost exact with the data for the 16 mm glass pane at this region right here. But still, it likewise overpredicts the transmission loss at higher frequencies. So at the end of the day, we're always better off measuring our new panel design to know exactly what we can deliver in terms of sound insulation between rooms. To summarize what we have learned, we find that the coincidence of projected acoustic and bending wavelengths leads to this increased sound transmission and thus low transmission loss over a mid to high frequency range. The panel composition determines the frequency range at which coincidence may occur, and the theoretical transmission loss above coincidence increases at 9 decibels per octave, but this is always a severe overprediction with respect to data. Practical data show an increase in transmission loss closer to the 6 decibels per octave that we likewise see in the mass law.
That's it for this video. In the next video, we'll learn about practical factors that affect transmission loss in real-world installations.